Greetings, everyone. I'm reading directly from the program. I'm supposed to say greetings, so greetings, everyone. We are going to deviate from the program in a moment here, but let's begin the program. Please continue eating your dessert. But let's begin the program. Except that I need to announce we have a new lost item now. We have a key that was lost. It's a key to a Ford. There's also a wine cork on the key ring and a giraffe. All right. So our first door prize of the evening will be a key to a Ford. There you go. We are seriously going to deviate from the program a bit. We're going to go straight to Rob's talk next because Rob needs his own computer because he's a Mac person and I'm a PC person. So this way we'll only have to swap once. But I am delighted that Rob agreed to fly across the country and join us this evening, and it's my pleasure to introduce Rob. Rob Gould is the Vice Chair for Undergraduate Program in the Department of Statistics at UCLA. He's also the Director of the Center for Teaching Statistics at UCLA. His bachelor's degree is from Harvey Mudd College, and his PhD is from the University of California at San Diego. And Rob has been extremely active in statistics education locally in Los Angeles, at the state level, at the national level, at the international level. Let me quickly mention three things that he's been involved in. He is a textbook author, and I saw his textbook on display right outside the door there if you want to look at it later today or tomorrow. Or buy it, Rob suggests. I don't know if that's an option, but perhaps it is. Second distinction I'll mention is that Rob is the founding editor of a journal called Technology Innovations in Statistics Education. And the third thing I'll mention, I don't quite know the noun to use, so I'll say that Rob is the originator of Data Fest, which started out at UCLA and is now a nationwide competition. But I'm very pleased, as I say, that Rob agreed to join us and give some after-dinner remarks. We had a negotiation about the timing of his remarks earlier. I don't think I'll reveal the result, and I'll tell you later how closely we come to the result of the negotiated time. But you can see Rob's title on the screen, and welcome, Rob.
Thanks. So Alan asked me to talk for 2 hours. But I said, no, that's far too much. In fact, when I asked Roxy for advice, and her advice was just keep it short. On the other hand, Alan's, yeah. You'll be crying soon. On the other hand, Alan said this is a great opportunity for me to express my opinion, so I'm going to compromise between short and opinions and talk fast. So what I thought I'd talk about is 8 years ago at the 2011 USCOTS, I gave a talk where I said that we had kind of a limited conception of the notion of data as educators. We relied on David Moore's wonderful definition of data as being numbers in context, and this was really helpful for us in many ways. But we now we still live in a day and age where data are more than just numbers. And our students know this, and they need to know more than just how to analyze data with numbers. And also the relationship between data and students had changed. So, as we know very well now, data, our personal data are now commodities, and we have a much more personal relationship with the data than we used to have. And so I argued that things had to change. And in that context, I gave myself a challenge, which looking back, now I see is pretty badly worded, but I'll reword it now. Basically, the challenge was I wanted students to bring into their intro stats class what they thought of as data, and they would learn to analyze it to learn something meaningful to them. So the idea was to not just give them the data that I thought of as data that I knew I could teach, but to force myself to learn to teach what they could brought in. So in any case, 8 years later, I thought this would be a good time to look back and see how it did. So I built this very complicated algorithm in which I could put in all of the data and monitor my progress. And this is actually more of a simulation than the actual calculation. But when I hit start, it's going to go ahead and do its little calculation. You can see it pretty well. So I'm not just longer than I thought. All right, so I think this is not bad, is how I'd categorize this. I mean, it's I think it's just barely borderline 0.05. It's trending towards 100%. So I think what I'd like to do is talk about why I think what I owe this tremendous progress to, but then a little more honestly reflect on what needs to be done to get higher up. So first thing I owe this to is I've been really lucky for the last 6 years to be lead principal investigator on something called the Mobilize Project. It's an NSF project. It's a lot to talk about, but at the simple version is it was the brainchild of a computer scientist at UCLA, Deborah Estrin, who left UCLA in 2014, and I took over her project when she left. And the goal of this project was to use something Deborah developed called participatory sensing, and to use it in high school classrooms. And participatory sensing is a data collection paradigm where people use cell phones to collect data. And that sounds mundane, but the idea is to create a community out of the data collection. So in citizen science, if you're familiar with that, we go out and we collect information about butterflies we've seen, and we send it all up to some butterfly expert who analyzes it, and we never see it. In participatory sensing, the data stays in the community, and the community analyzes the data. So this project was designed to try and get that into high school classrooms. And one of the main successes, perhaps the only success that came out of this, was a year-long course for high school students called Introduction to Data Science. So this course teaches data analysis using RStudio in high schools, and we collaborated. Our partners in this was LA Unified School District. So LA Unified is the second largest school district. It's an urban school district, one of the poorest populations in the country. Administratively just a mess. So I describe it as if Kafka and Dickens teamed up to write a horror novel. But it's reality, and so I mean, if it can work here, it can work anywhere. The success is owed to many of these lovely people who I don't have time to introduce, but at least one I'll come back to. But the other success builds off of what Jane was talking about this morning, is what we call the data cycle. So those of you with sharp eyes will see this as not far removed from the PPDAC, but it's really much closer to the 4 stages of the investigative cycle in the Gaze K-12 document. And like Jane found, we found great power in turning it into a visual. And the motivation for this was not to help students, it was to help the teachers help the students. Because most of the teachers in the beginning of this project were computer scientists, and what we found they would do is they would go and create classroom lessons that went something like, they would use the phones, they would collect lots of categorical data, their students would then make bar plots of the data, they would learn how to make each bar a different color, and then they would write a conclusion that said the blue bar was the tallest. And literally, I mean, there was some pride in this, that this was seen as a worthy outcome, and we couldn't figure out how to get them to go deeper until we started to kind of use this process in a very iconic, if that's the right word, visual sort of way. But guess which phase was the most important phase? Ask questions. So once we started to focus on getting them to ask questions, and we used Pip Arnold's research to develop a rubric that helped the teachers grade the questions, because that's really important, as you know, if you're a teacher, and also help students improve their questions, then things really kind of started to take off. It took a lot, I don't want to simplify it, it took a year's worth of professional development, but things really the students started to get deeper into the data. So this was the first secret of our success. The other project thing that I've been participating in, as Alan said, is Data Fest. And the Data Fest, interestingly, the very first one was just about 2 weeks before I gave the talk here in 2011. And it's grown a lot since then, thanks to many of you in this room. I should particularly single out Mina Shankankaya-Rundle, who is not in this room because she's just moved to Scotland. But she's really played a big role in expanding this. Those of you who have hosted a Data Fest know that if you listen to the teams as they work, you learn a lot. And what you learn is not always very pretty. And one thing I have continued to learn, really emphasizes the importance of asking questions. Because the teams that sit there and immediately start to generate models or start to print out lots of graphs and hope that some beautiful pattern is going to hit them between the eyes are the teams that don't do very well. And hopefully a visitor comes and steers them right. Whereas the teams that sit down and pose questions about the quality of the data, the source of the data, the meaning of the data, transitioning into questions about the process, those are the teams that have a winning strategy. So it kind of emphasizes, again, that importance of an explicit strategic plan and the importance of asking questions. As an educator, it really has hit home for me the importance of giving students really hard problems. I remember Deb Nolan wrote a paper about this a few years ago, and I never quite knew what to do with it. But I think really hard problems are really good. The final exam is a really bad time to give a really hard problem. So a safety net is a really important thing because that ability to fail and gives you permission to be creative. And so, I mean, I think one of the things to which I attribute any success in my progressometer is through giving students these hard problems. So I still have a long ways to go on my progressometer, and I have a little story that illustrates partly why I think I have a long ways to go. About a year ago, in my intro stats class, I gave them a project. So we're on the quarter system, so things go fast, and we have big classes, relatively big. I had 180 students in this class. And it's a tame version of the challenge I gave myself earlier. It's tame very much in the sense that Albert Kim means it. The data were from a vetted data repository. I worked with our librarian to come up with a safe space for data. And surprisingly enough, there's lots of data repositories that don't have data in them. So the main thing is to find one that did, or find several that did. We made sure that a large percentage of them had code books and that they were in fairly graspable formats. So the students got to choose any data set they wanted. They had data from the arts to the sciences to the political science, anything you could name. Download the data, that was the first 2 weeks. Pose some questions, describe the data, analyze the data. That was the quarter in a nutshell. Which phase do you think got us hung up? Phase one, the downloading phase, yeah. So, you know, there were lots of reasons. I kind of made a list of the reasons and excuses. I don't want to exaggerate. This wasn't the whole class. It wasn't even a majority. But when you have 180 students, you know, even 30% means a lot of annoyances, and it slows everything down. The basic problem here was students really were challenged by file management things. Where do the files go? What's this zip file? How do I unzip it? They were downloading everything and then not noting. I mean, I could go on and on. Anything you can imagine going wrong went wrong. And these are smart kids. I mean, we have good students. So I was frustrated that in the most tame version I could come up with of my challenge, I still couldn't succeed. We didn't really get past the second phase. So with that in mind, I've come up with 4 suggestions for moving forward. These suggestions are kind of for myself, but I'd also like to turn them over to the community as a whole. These are highly opinionated suggestions, but maybe if we make them, I can make more progress. So the first suggestion is to understand what the word data means. And by this, I don't mean that we need to come up with better definitions and put them in our syllabi or our textbooks, because we have good definitions. What I mean is we need to understand what the students mean, because the word means a lot more than we think it does. There's this great book by a librarian scientist called Big Data, Little Data, No Data, Christine Boardman. And she notes that there's something like over 80 different definitions of the word data kind of out in the literature right now. But let me just give you 2 examples of what I mean. So the first comes from a paper from Bill Finzer and Cliff Knold and Kosong, I think, Kitong. And this blurry photo is meant to be an illustration of traffic. And students were asked to organize the data in a table, or not in a table, but organize it in a meaningful way. And these were middle school through high school students. And what they found was the students didn't organize them as we do when we're preparing an analysis in a flat file format, they came up with a variety of creative ways. Younger students preferred narrative organizations. Most or many students had hierarchical organizations, and really only students who had taken a statistics class organized them in a spreadsheet style format. And the reason I think this has big implications is it shows that the thing we think students think about data, they don't think about. And that means that when we're beginning students' statistical voyage, giving them Excel spreadsheet style formats, flat file formats, we're starting them off on a foot that they're this is a bad metaphor. We're starting them off, in an uncomfortable place with a structure that's abstract to them, in which it's not necessarily clear how that structure relates to the process that generates the data. So it's a big eye-opener for me to understand that my lack of understanding of what students think about data is affecting what I'm teaching or how I'm teaching it. The other example I want to give, it was very interesting to me when I went into our library search engine and I searched for journal articles on data literacy, that the plurality of papers come from the information sciences and library sciences. So this is one such paper, this is a very brief summary, where they actually went out and interviewed teenagers and said, what does data mean? And their answer, they said that the answers were all over the map, but they divide them into these two camps that you see here. So one of them is kind of what we usually address in our stats course, the kind of scholarly, professional view of data. The others were this digital view. But what's a little dismaying is none of the students, or very few of the students, connected data to them personally, despite the fact that we know that data do matter to them or should matter to them and do affect them in very personal ways. So again, it's a realization that students are coming to us and we don't really know what they're thinking about it when it comes to data. And what I'm really trying to say with this here is we've spent a lot of time thinking about what requisites and knowledges students bring into the classroom, but we focused on math. Is it an algebra? Is it a calculus-based stats class? And we've spent in recent years more attention on any statistical misconceptions they may bring. But if our class is going to be centered on data, and if we're teaching data analysis, we need to know what conceptions about data they're bringing to the table so that we can decide if that's what we want them to know and how to move them along. And it'd be an interesting question to ask and discuss in the bar afterwards, what we want them to think about data, given that maybe this is where they're starting from. Another thing that we don't know much about when they come in is their computational skills. More of us are using computers to teach and are teaching coding, but we don't know what background they bring with them. So that leads me to my second suggestion, which is to become a nuisance in the nicest possible way to computer science educators. And there's a couple reasons. So first, if you don't know, there's a lot of really exciting things happening now in K through 12 computer science education. And here are just three big projects. The Mobilize project I worked on is a sister project to the Exploring Computer Science curriculum. All of these are big national endeavors that are increasing representation of women and students from groups that aren't fully represented in the sciences and are doing a good job of bringing them into the scientific fold. So there's a lot of great energy going on in these fields right now, so that's a good thing. The other thing is that they can teach our stats students computation so that we don't have to. But it's a two-way street. The Computer Science Teachers Association, maybe many of you know this and some of you don't, they have their own standards, and their standards include something they kindly call data and analysis, but it's really data analysis. And it includes statistical outcomes, and this is just, they have many, many, many of them, a page and a half or so of them. So to me, this is frustrating because I feel like once again, a profession external to ours is telling us or telling other people what to teach and how to teach it. But there's a real opportunity for collaboration here because, it's not as if computer science teachers in high schools are getting great statistical training and math teachers aren't. They're all going through the same pre-service and in-service programs, which we know can really neglect statistics. So we can offer them a lot of help here. They want to teach some statistical ideas. We're the experts in how to teach statistical ideas. We should make ourselves nuisances so that they know we're here. And on the plus side, they're the experts in teaching computation. We need our students to know computation. We should be reaching out to them and building some bridges so that they understand what our needs are from them as well. So I think there's a really potential, some great potential collaborations in this community. So the third suggestion is also about computation, and it's basically that we have a real need for assessment items that get at this computational issues. So I'm thinking that many of us, and I'm guilty of doing this at the high school level, teach R to introductory statistics students. And if the goal of your stats class is for students to learn R, then you have to teach it. But if you have lots of other goals, some of which are very complex and subtle and take a long time to develop, you may be concerned about whether the technology you're using is enhancing that learning or inhibiting that learning. It's probably not a yes or no, it's probably a sometimes, but where and when is that sometimes occurring? And I mention this because part of the challenge we face with this high school Introduction to Data Science course is there's no real way of understanding exactly what they're learning. It's exciting that in the past few years, our community has developed wonderful assessment tools for statistical understanding. I've circled the artist website there via cause, but that's just one example. Many of us have used the chaos inventory. There's lots of things that have really improved my teaching of statistical concepts. For our IDS project, we used Tim Jacoby's locus levels of conceptual understanding of statistics. It was beautiful for us because it aligns with the 4 steps in the GAZE K through 12, which maps onto our data cycle, but it misses things. So for example, it has a collect data inventory, and we have a consider data, and in consider data, they do more than collect data. They filter out unwanted observations, they condition on values, they transform variables, they create new variables. There's a lot going on there that's not captured in a statistical conceptual inventory that's really important. There are inventories that capture computational thinking, but they do so in a really broad sense, and it really doesn't capture that thinking that goes on when students are using computational thinking to analyze data. So I think we can't really answer the question about is using R a good thing or a bad thing with beginning students until we know until we can measure what it is we're wanting them to learn. So I think that is many of you out there there have been some great talks I know or breakout sessions on assessing instrument validity and people looking for PhD ideas. Here's a fertile area I think is really fertile. So go for it. So my fourth suggestion is also related to technology. It's to find a bridge between the gap of software for learning statistics and software for doing statistics. And so this is Amelia McNamara's idea. She mentions that there's lots of lots of software out there that help students learn to do. And of course, as professionals, we have our software that we do statistics. We want students to get into that far right column, and I believe, as someone who believes that every citizen needs to do data analysis, I believe every citizen needs to be doing some sort of professional level data analysis. I'm not quite sure yet what that means, but how do we get students from the left to the right? Computer scientists have Scratch, if you know that, that's this like symbolic visual coding language for children that is quite rich, but lets them develop basic ideas and then expands naturally into deeper languages. But we don't yet have a clear pathway from one to the other. Now, softwares are arriving. Datadesk is an old one, but it was partially filling that gap. So there is progress in developing software that fills the gap, but we also need pedagogy to get us across that gap. I think this is very much related to the assessment thing in number 3. We need to be better able to assess how computational and statistical thinking interact. so that we can kind of negotiate our way across that gap. So, what I've learned, so it's going to be much less than 2 hours. So just to summarize, we have to teach curiosity. We have to teach it in a very focused way. If what you're doing is called data science, scientists spend a lot of time learning to pose questions, and we need to teach that formally. And so this is one important lesson. You don't have to use the data cycle, but I think especially for beginners, to make the strategic steps explicit. Experts can break those steps, and even beginners break those steps. No one really cycles around in a clockwise way, but it's a useful guide map, and it's a useful strategic tool for students. And then we need to keep giving them hard problems in safe settings so that we understand where their failures are and they understand where their failures are. And the greatest lesson of DataFest is your worst students do far better than you can ever have imagined, and they do much better than they ever do in class. So just a summary of the steps. We want to understand what students think about when they think about data. We want to collaborate with our computer science colleagues. We want to measure the interaction, actually I want to have you measure the interaction of computational, I don't want to do this. I just want to have a web page that has it done. And we need to bridge the gap. And what I'm really confident in is if we do that and I can come back in 8 years, I'm thinking we may be as high as this. So thank you very much.